Hello, in this video we're going to provide an example of a function that is infinitely differentiable but is not analytic. So let me explain what this is all about. If you recall, what we did when we started discussing Taylor polynomials was that our goal was to approximate functions using polynomials. We talked about the contact of two functions, and we were able to find polynomials with high contact with a given function. Our goal was to show that if you take a function, then it would be the limit of its Taylor polynomials. In other words, Taylor polynomials, as you let n go to infinity, they approximate the function better and better. Under some circumstances, we were able to prove that. For some examples, for some functions like ln of 1 plus x, e to the x, and things of that sort, we were able to prove that in fact f of x is equal to its Taylor series. So the first thing that we need in order to be able to define Taylor series is our function. We need our function to be differentiable of all order. In other words, we need our function to be C infinity. However, this example shows that even if your function is C infinity, it may still not be equal to its Taylor series. So in other words, there is a function that has derivatives of all orders but is never equal to its Taylor series. So here is the statement of the theorem, the more rigorous statement of the theorem. Consider this function. It is e to the power of negative 1 over x squared when x is not 0, and it is 0 when x is 0. This function f has derivatives of all orders, but the only value of x for which f of x is equal to its Taylor series at 0 is x equals 0. So there's only one value, the center, the x equals 0, clearly both sides are going to be 0. But at any other point, the right side is 0, the left side is never 0. So what we want to show is in fact that fn of 0 is equal to 0 for all n. Okay, so we're going to go ahead and prove this one. But the proof of this is a little bit difficult. So what we're going to do is we're going to use the definition of derivative and prove that the first derivative is 0, and then we'll see how we can prove that. So as usual, I'll write down the strategy of the proof on the right, and then we'll write down the actual proof on the left. Okay, so f of 0 is clearly 0. That's how it is given. So I'm going to write down the derivative of f. The definition is f of x minus f of 0 over x. So if I look at that, f of x is e to the power of negative 1 over x squared, and the denominator is x, and f of 0 is 0. So I would need to show this is approaching 0. Another way of thinking about this is 1 over x over e to the power of 1 over x squared approaches 0 as x approaches 0. So if you look at the numerator is a polynomial of 1 over x. So if I call 1 over x, let's say t, then I would get, if I call this one t, then I would get t over e to the power of t squared. And I need to show this approaches 0 as t approaches infinity. So this is what I need to do. Okay, so in other words, I would need to show exponentials grow faster than polynomials. So how do we show this? The way we can show this one is by the fact that if you look at e to the power of t squared, we have the Taylor series for that. We know this is equal to the sum n equals 0 to infinity t squared to the power of n divided by n factorial. So this exponential is larger than every single one of these terms. For example, it is larger than t squared over 1 factorial. And if you divide by t, you'll get what you want. So you get e to the t squared over, since I want to make sure that I'm dividing by a positive number, I'll divide by absolute value of t. And then I flip it, so I get t over e to the t squared in absolute value is less than or equal to 1 over t. And since t goes to infinity, this goes to 0. And then by comparison lemma, this would also go to 0. So that's the process for showing that f prime is 0. F prime of 0 is 0. So now I will look at f double prime and see what I can do, and then we'll write down the proof, see what we need to prove, and then we'll write down the proof. So far we showed that f prime of 0 is 0. So now let's look at f double prime of 0. This is the limit as x approaches 0, f prime of x minus f prime of 0 divided by x. Okay, so in order to be able to prove that is 0, I need f prime of 0. F prime of 0 we already showed that it is 0. So I need f prime of x. F prime of x, since x is not 0, I can take the derivative of the function. Derivative of the function is exponential, so it's e to the power negative 1 over x squared times derivative of that, which is 2 over x cubed. So I would need to show this approaches 0. And if I evaluate this, this would be e to the power of 1 over x squared at the bottom, and then 2 over x to the 4 on top. So I would need to show this is 0. If I take 1 over x and call it t, then I would get the limit as t approaches infinity of 2t to the 4th over t e to the power of t squared is equal to 0. In other words, again, I have to show the exponential grows faster than polynomial. And how do I do that? Pretty simple. All I need to do is to apply the exact same strategy. E to the power of x squared is the same as t squared over to the power of n over n factorial. Now, I need to compare it to t to the power of 4. But I want to show it actually goes to 0. So I need a power that is larger than 4. So I will choose the next one. So this is more than t to the power of 6 over 3 factorial. And then you do the same thing. So t to the power of 4 over e to the power of t squared would be less than or equal to t squared 3 factorial over t squared, I believe. And since t goes to infinity, this goes to 0, and therefore this goes to 0. Okay, so let's see if we can build the same strategy to show that the next one is also 0. So now if you want to find f triple prime of 0, you'll have to do the same thing. F double prime of x minus f double prime of 0 divided by x as x approaches 0. We know this is 0 because we just showed it. We need a formula for f double prime of x. And if you look at f double prime of x, you take the previous one, which was e to the power of negative 1 over x squared times 2 over x cubed, and then you differentiate that. And then you have to use product rule. So when you use product rule, it becomes quite messy. And it becomes actually more and more and more complicated when you do the next derivatives. E to the power of negative 1 over x squared, and then minus 6 over x to the power of 4th. But really what matters is that this is e to the power of negative 1 over x squared times a polynomial of 1 over x. So it's 4 over x to the 6 minus 6 over x to the 4th. So this is a polynomial of 1 over x. If you take this quantity, this is 4 times 1 over x to the power of 6 minus 6 times 1 over x to the power of 4. And regardless of what the polynomial is, if we show that e to the power of negative x squared goes to 0 faster than any polynomial of 1 over x as x approaches 0, then we would be able to show that this product approaches 0. So that's what we need to do. So a few steps that we need to take. First, we need to understand the derivative of f. Next, we need to understand the relation between e to the power of negative 1 over x squared and powers of x. Okay, so we will write down the proof and we will break it down into multiple steps. So step 1, we will prove by induction on n that for every natural number n, there is a polynomial, let's call that Pn of x, such that Fn of x is equal to e to the negative 1 over x squared times Pn of 1 over x for all x that are non-zero. So derivative of every derivative of f at every non-zero point is e to the power of negative 1 over x squared times a polynomial of 1 over x. So basis step gives us f prime of x is equal to, by the chain rule, e to the power of negative 1 over x squared 2 over x cubed. By the chain rule, so if we set, we need a polynomial of 1 over x, so p1 of x would be 2x cubed. Then f prime of x becomes e to the negative 1 over x squared times p1 of 1 over x. So that is the basis step. Now we'll look at the inductive step. Suppose Fn of x is equal to e to the negative 1 over x squared Pn of 1 over x for a polynomial Pn and for all non-zero x. Now we're going to go over this and we're going to take the derivative of that to get the next one. So by the product rule and the chain rule, next derivative of f is e to the negative 1 over x squared 2 over x cubed Pn of 1 over x plus there's also a negative sign, or no, there is no negative sign in fact, plus e to the negative 1 over x squared times Pn prime of 1 over x times negative 1 over x squared. And this is equal to e to the negative 1 over x squared times 2 over x cubed Pn of 1 over x minus Pn prime of 1 over x times 1 over x squared. Now, if we set Pn plus 1 of x as 2x cubed Pn of x minus Pn prime of x times x squared, then Fn plus 1 of x becomes e to the negative 1 over x squared Pn plus 1 of 1 over x. So all I did was I replaced all of the 1 over x, every 1 over x with x. And since 2x cubed Pn prime and x squared are polynomials, so is Pn plus 1. Because if you look at Pn plus 1, it's a product of polynomials and sum of polynomials. So it's polynomial 2x cubed times polynomial Pn minus polynomial Pn prime times x squared. So that would be a polynomial. So this completes the proof. Okay, so step 2. In step 2, we're going to prove the limit is going to be 0. So for every n in n, the limit of, as x approaches 0, of e to the negative 1 over x squared over x to the n is in fact 0. We want to show these quantities always give us 0. Okay, so how do we prove this? We are going to do that by the Taylor series for e to the power of x. So by an example, e to the power of t would be the sum t to the power of k over k factorial, k equals 0 to infinity. Okay, and this is for all t in R. So that means for every non-zero x, e to the power of 1 over x squared would be the sum k equals 0 to infinity 1 over x squared to the power of k over k factorial. Now take some integer more than n, maybe just n plus 1. This would be greater than or equal to 1 over x squared to the power of n plus 1 over n plus 1 factorial. So that means if I take the reciprocal of both sides, I get e to the power of negative 1 over x squared is less than or equal to x to the power of 2n plus 2. If I take the reciprocal of the numerator, and then times n plus 1 factorial. So this is what I get on that side. Now I'm going to divide by x to the power of n. However, I'm going to divide by absolute value of x to the power of n to make sure I'm not, I don't have to worry about flipping the direction of inequality. So e to the power of negative 1 over x squared divided by absolute value of x to the power of n is less than or equal to absolute value of x to the power of n plus 2 times n plus 1 factorial. Now, limit of n plus 1 factorial times absolute value of x to the power of n plus 2 is 0 as x approaches 0, since absolute value of x to the power of n plus 2 is continuous. So by this squeeze theorem, limit of e to the power of negative 1 over x squared over x to the power of n as x approaches 0 would be 0. So you could rewrite that if you want to like turn it into exactly the way squeeze theorem looks like, which would be a good idea. You could rewrite it as this is less than or equal to n plus 1 factorial absolute value of x to the power of n plus 2, and on the other side it's negative n plus 1 factorial absolute value of x to the power of n plus 2. Both of these two approach 0. This side and this side both approach 0. Therefore, the one in the middle also approaches 0. Okay, so this completes the proof of step 2. So now we are at a position that we can combine these two to prove that fn of 0 is 0 for every n. So step 3. We will prove by induction on n that fn of 0 is equal to 0. Okay, so first of all, for n equals 0, that's just f of 0 equals 0 is given. So basis step would be for n equals 0, f of 0 equals 0 is given. So now we're going to use the inductive step. Okay, so suppose we know fn of 0 is 0 for some n. By definition of derivative, fn plus 1 of 0 becomes the limit as x approaches 0 of fn of x minus fn of 0 over x. If you look at fn of 0, that's just 0. And if you look at fn of x, we know by step 1 what fn of x is. So by step 1, fn of x is Pn of 1 over x times e to the negative 1 over x squared for some polynomial Pn. By inductive hypothesis, fn of 0 is 0. So let's say this polynomial Pn has some specific form. So suppose Pn of, let me call it z, is equal to the sum Cj z to the j equals 0 to, let's say, L. If you look at fn of x minus fn of 0 divided by x, this becomes Pn of 1 over x e to the negative 1 over x squared divided by x, because fn of 0 is 0. I'm going to replace Pn by its formula. So it's the sum j equals 0 to L Cj. I have to replace z by 1 over x. So 1 over x to the power of j e to the power of negative 1 over x squared, and then divided by x. Now notice that this expression is approaching 0 by step 2. So this is Cj e to the negative 1 over x squared divided by x to the power of j plus 1. By step 2, limit of e to the power of negative 1 over x squared over x to the power of j plus 1 is 0 as x approaches 0. Therefore, fn plus 1 of 0 is going to be 0, because fn plus 1 was the limit of this polynomial multiplied by limit of basically that fraction, fn of x minus fn of 0 over x. So that approaches 0. So this shows that fn of 0 is 0. So therefore, fn of 0 is 0 for all n. Okay, so this proves the furthermore part, in fact. So it proves this part. We prove the furthermore fn of 0 is 0. Now let's look at the Taylor polynomial, Taylor series. The Taylor series for f at 0 is the sum fn of 0 over n factorial x to the power of n equals 0 to infinity. But all of these are 0. All of the fn's, all of the derivatives are 0. However, fn of x, f of x is equal to e to the power of negative 1 over x squared, which is not 0, for every x that is non-zero. So thus, for every non-zero x, f of x is not equal to its Taylor series. And that's the end of the proof. Notice that the right hand side, when you plug in x equals 0, is 0. So there is no way that a Taylor series cannot be equal to its value at the center. When you plug in the center, you're always going to get x0, f of x0. So that point, you cannot avoid it. Every other point, the Taylor series and the function are actually quite different. They are not the same. Okay, this is a very interesting example because it shows that even though this function is completely differentiable, C infinity, it is not equal to its Taylor series anywhere. except for the center. This kind of function is in fact something that we would like to avoid in many instances. So if a function f from R to R is equal to its Taylor series centered at 0, then the function is called analytic. And what we showed in this example is that there is a function that is not analytic, but it is infinitely differentiable. Okay, so this brings me to the end of the video. So if you would like to continue with this topic, feel free to subscribe, and I will see you in the next video.